So it's finally time for us to invoke Stokes' theorem. And to do that, we're being given a circulation integral around a closed curve in three-dimensional space. And instead of evaluating it as a circulation integral, what we want to do is fill in that closed curve with some surface. And again, it doesn't matter what surface we choose as long as it has the right boundary, namely the boundary that is our closed curve. And then finding the surface integral of the vector curl of our vector field through that surface with a normal vector oriented according to the right-hand rule, so that the normal vector points in the direction of your right thumb if your right fingers curl in the direction that the circulation is intended to be positive. So the problem that we'll work on here is activity 1295, part B. And that activity has us doing the circulation of this vector field, 3z squared I minus z squared plus 2xj. I assume there should be parentheses around z squared minus z squared plus 2x plus zyk along the circle in the xy plane of radius 3, centered at the origin, assuming the counterclockwise orientation for that circle. So let's work on this part B. This is, by the way, an example that we might want to do more than once. Because this curve, this particular curve that we're using, is actually a curve in the xy plane. And so there exists a surface that resides only in the xy plane that would have that curve as its boundary. And so instead of Stokes' theorem, we would actually have the option to use Green's theorem instead. So if you choose your surface to be just something flat inside the xy plane, you should find out that what Stokes' theorem does is it spits out the same thing that you would have gotten with Green's theorem. So I think this is probably a good place to start the work on this problem, is to imagine that you're filling in this curve, which this curve resides just in the xy plane. Fill in the curve with a flat portion of the xy plane, and then when you apply Stokes' theorem to that surface with a normal vector facing in the positive z direction, you should see that Green's theorem will pop out in some fashion or another. So I think that's probably the place that we ought to start on this last problem that we'll do together during class. So the first thing that we decided to do with this circle of radius 3 oriented counterclockwise in the xy plane is we decided let's make it a flat surface, and then Stokes' theorem would tell us that the flux through that surface with the normal vectors oriented upwards, so I have this whole forest of normal vector trees here that's pointing upwards because of the right-hand rule, once again, that upward flux will give us the same value as the counterclockwise circulation. And so when we go to do the parameterization to get us there, we parameterize the boundary curve. Let's switch over to here. Boundary curve, 2 cosine s, 2 sine s, comma 0, 0 to 2 pi on that parameter s. That gives me that black circle, right? But then the surface itself is the disk of radius 2 centered at the origin in the xy plane, which we can parameterize with t cosine s, t sine s, comma 0. With t ranging from 0 to 2. So it's just like you're taking this 2, which is the radius in the xy plane, and just letting it vary from 0 to 2, instead of fixing it at 2, which just gives you the edge. And when you find a normal vector for that, you take the cross product of the partial derivatives, take a look at your normal vector. 0, 0, minus t. So what's the problem with that? So we wanted normal vectors to point upwards according to the right-hand rule, but when we did this calculation, we ended up with a normal vector 0, 0, minus t because t is non-negative. Those normal vectors are all pointing downward, not upward. Mm-hmm. So how should we fix that?
We could just multiply by -1.
Yeah, just flip it. All we need to do is flip it.
-1.
So multiply it by -1. And another way to say that would be just to reverse the roles of s and t, right? Because that's where the arbitrary choice comes in your parameterization. You chose t cosine s, t sine s. We could have done s cosine t, s sine t, and parameterized exactly the same thing, right? So that's why we have this little step, this consistency check, before we go forward with our integral. Instead of doing rs cross rt, we'll do rt cross rs. And we're going to end up with the same thing, but with a minus sign, without that minus sign as part of my normal vector. Because when we do a cross product in the opposite order, that's the same thing as multiplying the cross product by -1. There we go. So edit that out. That's my normal vector that points upward, which is exactly what we wanted. And so then the upward flux through the surface is going to be given by that surface integral. The integral on the disk of the curl of G, curl, whoops, curl of G dot, whoops, just one dot, with the normal vector, which is 0, 0, t. And we'll integrate that ds dt. Okay, let's make this calculation the last thing that we do today. After we do this dot product, we end up with a fairly nice double integral, the double integral of 2t ds dt. And the region over which this integral is being taken is s ranging from 0 to 2 pi, and t ranging from 0 to 2. Well, where would this 2t have come from? Sort of, what is this 2t kind of representing for us? Let me think about this in a slightly different way. Let's suppose that we take that t. What was t playing the role of here, by the way, in our parameterization?
T was the parameter for the radius of the circle.
Yeah, t was the parameter that looks like the radius of the circle. So t ds dt sounds an awful lot like r dr d theta of 2 times r dr d theta. Right, so I'm kind of making a allusion here to what this would look like. But what is r dr d theta if we convert it back into rectangular coordinates?
Dy dz. No, dy dx.
Dy dx. So this is the double integral of 2 dy dx. Right. And so now I might ask the question, well, where would that 2 have come from? Like, why should we have expected that 2 was the right thing? Well, remember that we explicitly kind of chose a surface that was a part of the xy plane, right? And my surface, because it's part of the xy plane, has z equal to 0 everywhere. And if z is equal to 0 for my vector field, so here's the point that I want to make about this. On the xy plane, where z is equal to 0, we have that the vector field G of xy 0 has the form, what is that, 3 times 0 squared, which is 0, and then 0 squared plus 2x, so 0 comma 2x comma zy, which is 0. Once again, so that's what my vector field looks like as a vector field on the xy plane. And actually my vector field is parallel to the xy plane when it's on the xy plane, right? Because of this 0 component in the z. And since my vector field is also parallel to the xy plane in this example, this whole thing reduces down to a problem on the xy plane. We didn't need 3 dimensions to do this particular example, right? And if I do that, what I'm saying is this is really the same as the 2-dimensional circulation of the vector field that's just 0 comma 2x. Let me call that f. 0 comma 2x. Where that circulation is taken around the counterclockwise circle. Circle of radius 2. Now, what would we do according to Green's theorem? That is the same as what? Load up my favorite toy illustration one last time, right? Green's theorem tells us that if our integral is just in the xy plane, that the circulation around a closed curve is the same as the double integral of the scalar curl. Right? So this is going to give us a chance to relate the vector curl that we computed with a scalar curl that we would be computing right here. So it would be the double integral, again on the disk of radius 2, so x squared plus y squared less than or equal to 4, of the scalar curl of this function, nabla star. And this vector field is 0 comma 2x dx dy, or however you'd like to do that. But what is the scalar curl of the vector field 0, comma 2x?
Just 2.
It's 2. It's the x partial derivative of the y component, which is 2, minus the y partial derivative of the x component, which is 0. And oh look, we get the exact same integral popping out of Green's theorem as we got popping out of Stokes' theorem in this example. It's just twice the area of that disk, right? It's the, or rather, hold on a second. My region of integration is a little bit different here. X squared plus y squared less than or equal to 4. Right. So if we were to continue from here, we would end up converting this integral over into polar coordinates, and then we would have exactly what we had before. Integral from 0 to 2 pi with respect to theta, and an integral with respect to r that goes from 0 to 2. And the integrand is 2, but then dy dx is going to turn into r times dr d theta. And now we have exactly the integral that we had before. So Green's theorem pops us out the same answer that Stokes' theorem would have, which is reassuring, right? And so all we need to do here to finish this up is just to do this evaluation, and then we will be done. Oh, I think I see what I did here. What was confusing me is that this d is not the same as that d. This is the x squared plus y squared less than or equal to 4. There we go. So this is just twice the area of the disk of radius 2. So it's twice times pi 2 squared. So what is that, 8 pi? Done and done.
You equal to 25.
Having evaluated this integral, just it's twice the area of that disk, evaluates to 8 pi. That's where we're going to leave things for today.